solderability test methods, both dip and look and wetting balance methods, what the motivation is behind the need to hot solder dip components, and how the new J Standard 001 RevF impacts you and your company. There's somewhat of a misconception out there that it's only for the mill aero people, and you'll find that with the change from Rev E to F, that is not the case anymore. Okay, so here are the topics we're going to cover. We're going to talk about the various test protocols for solderability, some of the standards, the more common test standards for solderability testing. I'm going to briefly touch on tin whisker mitigation, also gold embrittlement and gold removal. For those of you who are doing end-of-life builds, we're going to cover legacy components and then also RoHS conversion. We're going to talk about the supply chain of components for both RoHS and tin lead. Briefly touch on the GIA retinning requirements, discuss coplanarity and solder thickness when doing retinning, and then also give you some examples of surface mount and through-hole retinning, and we're going to have a few videos as well to show. As I mentioned before, there is some people have a confusion between what is solderability testing and component retinning. They're two different issues. Solderability testing is designed to determine how well molten solder wets on solderable surfaces. The most common categories of solderability testing are either a qualitative and a quantitative test method. Component retinning, however, is not the same as testing. It is the process of dipping electronic component terminations in a bath of molten solder. What it does is, in addition to providing a fresh intermetallic layer of new virgin solder, if you will, over the base metal, it removes oxides, it removes gold, and provides a very good solderable, highly solderable surface. So they're two different issues. So again, sometimes people ask, what is solderability testing? It is not component preconditioning. We've seen cases where people may buy a solderability tester and attempt to use it for component reconditioning or tinning. That is not the case. You wouldn't do it because it has a single static solder pot. So anything you remove, oxides, contaminants, gold, etc., is going to stay within that solder, and it's not flowing. It's a static pot. So it's not recommended to use that for component conditioning. So solderability testing is a measure of the ease at which a solder joint can be formed. And it's primarily used to assess the solderability of device package terminations. For example, if you're getting a component from 2 or 3 different vendors, it's a good idea to do periodic testing when you're doing your qualification, which vendor is producing or shipping to you the most solderable, highly solderable components. And again, solderability for a given component will vary depending on the type of solder alloy you use. For example, solderability with lead-free alloys, whether it's SAC 305 or SN100, is going to differ significantly than the solderability when you're using lead-based alloys, because we all know lead, even though it's a bad material, tends to wet very, very easily. Okay, there's primarily two different solderability test methods. There's the dip and look method and the wetting balance method. We had some questions in the first session today, which one is better? And the answer is, they're two different things, two different purposes. The dip and look method is a qualitative type. It's subjective versus on comparative analysis. We'll show you some examples in upcoming slides. There's 2 suppliers that dip and look test equipment. Wetting balance is a quantitative type test where you actually have a test instrument that gives you a plot, and a human being interprets that plot, much like an X-ray. You have a beautiful, great 2D X-ray system, and it gives you a really nice image, and you control the kilovolts and the power and oblique angle view and everything else. But it comes down to a human being interpreting that image, or in this case, interpreting the curve. There are several suppliers of wetting balance systems. Again, we'll talk about it later. There's a place for both of them. For solderability testing, if you can use steam aging for accelerated life testing. If you want to simulate, for example, what happens if you keep parts on the shelf for 5 years or longer, it's a good idea to use steam age testing. It simulates accelerated life. We've seen people with components that are sitting on the shelf as long as 15 years for end-of-life build. So concern there is about the degree of oxidation. The dip and look method, as we mentioned earlier, is subjective via comparative analysis. But let me just talk right now the difference between dip and look and wetting balance. Dip and look testers are typically lower in cost, about 15, 16K. They're relatively fast test, easy to do. It is subjective, but it can be done on the shop floor by shop floor personnel. So it's something like doing an AQL. If you want to do a quick test on your production, a dip and look method is great for that. The wetting balance tester, it provides a much more precise test. It measures the wetting forces between the molten solder and the test specimen as a function of time. Cost there is a little bit more in cost. It's about 55, 60K, and it needs a skilled technician to do in the lab environment. It takes maybe about 45 minutes or so to really do a good wetting balance test. So it's something you're not going to do out on the shop floor. So there's a place for both. One is a good lab test, and the other one is a good periodic sampling on an ongoing basis. So one isn't better than the other. They're just two different test methods, and we'll give you in future slides, we'll show you the difference between the two. You can also use XRF to measure the solder thickness after you've done the retinning. Again, it's recommended at least 150 microinches or greater is recommended. Will easily pass accelerated life testing if you're looking for 5-10 year shelf life. You can also use scanning electron microscope if needed to look at the intermetallic layer once you've tinned the parts. This is how a dip and look test method functions. You basically take a specimen and it's dipped into flux for a predetermined dwell time, immersion depth, and then you dip it into a molten solder bath, again for a predetermined dwell and immersion depth. And after the specimen comes out, a human being looks at it. It's a subjective test. And the images on the left, you'll see the two that they accept. That's a condition where the solder has wetted at least 95% of, in this case, it's 25,000 diameter pin. That's under 10x magnification. So you dip the part in the molten solder, and then the human being looks at, or does it have 95% coverage? The two images on the far left show more pinholes, and they're a reject because there's less than 95% coverage. So it's a subjective test, but it's very quick. You can do it very quickly on the shop floor, and basically shop floor personnel can do it. You can also use 20 or 40x magnification, those images on the right. You can easily see non-wetting or de-wetted conditions. It's easier to do it here than after you build a circuit board or you're trying to solder a part that just won't solder and you're struggling with it. It's easier to do this to determine is it acceptable or not before you assemble a board. Here's some examples of after a dip and look test. The image in the upper left shows solderable coverage that's greater than 95%. Image at the bottom shows inconsistent solder coverage, very bad wettability. You can see gaps and inconsistent. So that's probably, again, bad terminations, a lot of oxides and sitting on the shelf for a long time. The upper right-hand image, you can see that's a component that was retinned, and you can see how the homogeneous intermetallic coating and what a good coating would look like. That's closer to 100% than 95%. The wetting balance test method is different in that we said it's a little more complex to run, but it gives you a very precise reading. The way it works is you dip a component in flux. The component then is attached to a device on a load cell, and the component is lowered into molten solder. And what you're doing is measuring the buoyancy of the device. In other words, what you're doing actually is measuring the speed at which the solder meniscus climbs upward or flows on the body of the termination. And basically, the better the solderability, the faster it will rise up. The solder meniscus will rise up on the termination. This says typical wetting curve. I'd like to call it an ideal wetting curve. You can see this is a measurement with a load cell where the part has been immersed into molten solder, and it will very rapidly, the meniscus rises on it. And that's an ideal situation. That's a very pristine part that would solder very, very well in a circuit board. Here's an example of using a wetting balance test to measure the difference before and after retinning. In other words, why do you need to tin parts? Tin parts are retinned for a variety of reasons: to remove oxides, to remove contaminants, to remove the gold. This was an actual case where it was a specialized component and the client could not solder in the circuit board. It just, I don't know if it was hand soldered or machine soldered, they just couldn't get it to solder. And it was from an offshore supplier, and the pins of the part were tested, and you see in blue that plot was done before retinning, and you can see that it was very slow. The meniscus rose very slowly. You can see the curve very, very slowly to get back up to neutral buoyancy, and it was a very slow wetting curve. That was basically, that's a slow or retarded wetting situation. That would be a case where it would be very difficult to solder that part in the board, if at all. That component then, or we took, I think it was 10 or 20 samples, we retinned them, or basically stripped off the original plating or tinning that came from the component supplier, put a new fresh coat of solder on, and did a second wetting balance test, and you can see the line in black. The meniscus rose very quickly, and you can see the before and after difference, the advantage of retinning a part as far as solderability. There are several solderability test methods, however, the MIL standard 883 and the J standard 002 are the most common. There are others. Some may apply to you, some may not. The top two are the most common in use. What's the motivation behind lead tinning or retinning? It's really improved reliability. With the new REV-F, there is a big need to do gold removal or gold plating. It's sometimes referred, some people refer to it as gold washing. Remove the gold. Also for tin whisker mitigation, which is a major concern for military or aerospace manufacturers. The other advantage of retinning or lead tinning is that it provides enhanced solderability. It produces a homogeneous intermetallic layer with the base metal or the component lead or termination. And if you look at it, what was the driving force behind the change from REV-E to F? It was lead-free and gold removal, and we'll show you some other slides coming up. Tin whiskers, I'm not going to dwell on it a long time, but it's well known that tin whisker growth is predominantly outward from the plated surfaces. That's why tin plating is typically not good in certain harsh environments. Tin whiskers can and do cause short circuits and arcing. Here's some graphic difference on a crystal oscillator. It's a little hard to tell, but if you look at the red horizontal line, these parts were retinned. Below the line is where they were retinned, and you can see no tin whiskers, and you can see tin whisker growth above it where they were not immersed. The pin was not immersed in solder. You can see it a little bit better on the bottom image, that once you solder dip, remove the tin plating and replace it with a homogeneous tin lead plating, you can see there is no growth of tin whiskers. As we mentioned, gold embrittlement, gold removal is a very hot topic now, especially because of the new REV-F with the J standard 001. You know, gold plating has been used a long time in the industry because it protects device termination through the harsh, high reliability qualification process. However, the issue is gold in a solder joint can create gold embrittlement. Pre-tinning or retinning removes gold as it's solubilized in the molten solder of the first of two solder pots. In other words, it's removed in the first pot, and then the component or the termination is retinned in the second pot. We'll show you that in another slide coming up. So why is gold used in the first place? Well, immersion gold over a copper base metal is highly resistant to the effects of corrosion. Gold is not oxidized and provides a very good protective layer over base metal. It provides a highly soluble surface, And the reason device manufacturers like it, the gold provides a very bondable surface for both gold and aluminum wire bonding. However, the inclusion of gold in a solder joint can result in gold embrittlement because that gold is going to be combined with other metals within that solder joint. So it's good for bonding and assembling the device, but when you get to the circuit board level, excessive amount of gold is not a good thing to have. So here again is some other examples of, why gold is being used. It's very good for gold wire bonding, gold-plated lead frames, and we see gold in eating boards. So that's nice, but we have to remember that once we get to the pinout stage, where we're assembling the board, assembling the device on the circuit board, gold has to be controlled to stay below a certain level. So again, some of the properties of gold: it doesn't oxidize very readily, it melts at a low temperature, which is good, but in a way it's bad because it dissolves rapidly during the soldering process. So the remaining gold in the solder joint can weaken the integrity of the interconnection. So if the gold dissolution is excessive during the solder alloy liquidus phase change, it can alter the composition and mechanical properties of the resulting solder joint. So gold embrittlement has been known to be a failure mechanism in tin lead for some time. Again, it's the amount of gold that is a concern, and that amount of gold comes from a variety of sources. Again, you can be concerned if you have ENIC boards, depending on the amount of electroless nickel immersion gold. That gold is a contributing factor to gold amount. Studies have been done, a variety of studies showing that SAC 305 tends to be maintains its proper mechanical properties a little bit better than tin lead, primarily because of the additional tin content. However, SAC 305 solder joints do degrade with increased gold content. So there's been all sorts of independent studies done, and the key is, what's the threshold, the maximum amount of gold? Well, as we said, does not appear to be a threshold. It's acceptable, unacceptable, good and bad. There's been kind of a debate within the industry: is 3% gold by weight the limit? Is it 5%? Some people the decision was made. The deciding agreed upon was 5% gold by weight is the maximum level within a solder joint. However, some people have seen gold embrittlement with gold levels as low as 1 or 2%. So it's a debate of high, it's a topic of high debate. Again, you have to realize you want to stay below 5% of gold by weight, and as device pitch gets smaller and smaller, those solder joints get smaller and smaller, the amount of gold is going to be increased because the total volume of the solder joint is therefore decreased. What's the reason behind gold removal? Well, for high-rel applications, solderability is no longer an option for many high-rel segments, not only Class 3, not only military, aerospace, or wellhead electronics, but also Class 2. So with the implementation of the new RevF of J Standard 001, solderability testing, gold removal, component retinning have become prerequisites for doing business in the global marketplace. It's kind of becoming more and more known, and we'll show you that in an upcoming slide. As we have found out going across the industry, I'm not trying to categorize everybody into one or two groups, but we have seen quite a few in the companies that fall in these two categories. Many manufacturer commercial electronics seem to feel that Class 2 products, they don't realize that RevF of the J Standard 001 affects them. It does. The new RevF does. And therefore, there are some people producing commercial electronics that don't realize that the nature or the reason for gold removal. People are becoming more aware of that. I believe the RevF was issued about a year and a half ago. It's now just starting to become more in the forefront. People in the military aerospace industry, many are doing things correctly. However, traveling around the country, we have seen, not going to name names, but we've seen many in the military aerospace industry that are still living in the 80s, and they rely on the MIL 883, and they're unaware of the newer GIA standard. We've seen many in the military aerospace OEMs still using single or static solder pots or both. They're dipping parts in a static solder pot with the tweezers, and they are, if you will, that's not a good way. You are not doing gold removal and oxide. You're relieving those gold material contaminants and oxides in that pot for when you're going to apply solder another time. We'll show you other slides on that. This is an excerpt right from the IPC standard that was issued, and there it is in 2014. And these are just the defect codes. I think everyone's familiar with these. N is no requirement, not applicable. A is acceptable. P is process indicator. D is defect. And again, you'll notice in the examples it varies depending on if it's class 1, class 2, class 3. What many people sort of glossed over, I believe, was that with Rev F, gold removal, again, it's not applicable to class 1, but it formerly was a process indicator for class 2 products. It's now a defect for class 2. It always was a defect for class 3. So the point is gold removal does now affect class 2 products as well. The J standard 001 Rev F basically states that at least 90 gold should be removed from at least 95% of surfaces through all components that have more than 100 microinches of gold thickness. You have to remove gold from 95% of the surfaces on all surface mount parts, regardless of gold thickness. You may ask yourself, how do you remove 95% of gold? The answer is you remove it all. You dip it and you remove all of the gold. And some people, there's a debate whether you have 100 microinches, whether you have 80, whether you have 120. And the answer is, on surface mount, you have to do it on all components, regardless of thickness, through hole. There's a debate whether, you want the spec says anything more than 100 microinches. We're seeing people removing it on all through hole, regardless of the thickness as well. You should remove it on all the solder terminations, again, anything more than 100 microinches. And a double tinning process or dynamic solder wave is required to remove gold, and we'll show you that in a couple of upcoming slides. And improper gold removal on leads and terminations prior to assembly can lead to cracks, solder cracks, or failures. For those of you doing end-of-life build, we've seen customers who have legacy parts that have been sitting on the shelf up to like 15 years. A lot of those are obsolete parts that come through distribution, and they are very heavily oxidized. They have to be retinned just to remove the amount of oxides, not necessarily for gold removal, but just because they are so poorly oxidized and result in sunken solder joints, non-wetting, de-wetting. So again, the need to solder dip components, you want to replace oxided, heavily oxided plated finishes that are unsolderable with an intermetallic homogeneous finish that's going to be impervious to oxide growth. You do want to eliminate or mitigate tin whiskers. You want to remove gold in preparation for high rel soldering, and you can argue that it's high rel in class 2. You can also solder dip components to convert a tin lead to a lead free. We're not seeing a lot of people doing that, but it can be done. We are seeing quite a few people convert RoHS parts to a tin lead finish for high rel applications, and the next slide shows that, illustrates that quite well. This is a view of the global supply chain, and we know we're living in a lead-free world, and if you look out several years, the estimate is that lead-free or tin lead parts are going to be down to 1 or 2% of the mainstream. So if you're in the military aerospace and you cannot use lead-free parts, the answer is you're going to have to retin them to remove the RoHS or lead-free finish and put on tin lead. The bottom chart shows you a breakdown of what is being retinned, and you'll notice the largest sector is lead frames, and that's again primarily because those device manufacturers very much want gold plating because it helps them for the bondability, but now the gold has to be removed off the lead frame before board level assembly. The GIA standard requirement states that robotic and semi-automatic solder dipping apparatus shall have controlled dwell time and depth of immersion, exit speed, Piece parts should be preheated to greater than 71 degrees C prior to solder dipping. Molten solder contact shall not exceed 2 seconds for the J standard 001 space addendum. And again, total immersion time should be less than 5 seconds per side, basically at all times. I wouldn't exceed 5. To achieve an intermetallic when you're doing retinning, we recommend that you test the component solderability with a wetting balance tester before you even do solder tinning. It's a good idea to know what that part is like before you tin it. We, as a matter of practice, measure the solderability before and after we do any retinning. You may have to pre-clean suspected components, remove organics and excessive oxides. We have seen quite a few connectors that have mold release on them, and you have to remove that prior to retinning because it's an organic compound. You need to use a flux that's specific to the component lead and termination finish. Preheating is generally required. We show that in a slide coming up. It's recommended to use a 2-pot system where the first pot will scrub or remove the unwanted plating, gold, or oxides. You want to keep all those material, the oxide, the gold, etc. You want to keep that in the first pot and not pollute the second pot. The second pot is used to apply a pure alloy finish coat, and you need to control the solder immersion speed, the depth, and extraction speed. This is an example of what a 2-pot system is like. Dual dynamic solder pots are recommended better than static pots. Nitrogen nerding is generally recommended because it helps mitigate icicles and dross. Flux application and preheating should be controlled. And you want to, again, use a scrubbing action in that first solder pot because you want to aggressively remove the oxides or gold. And you want to use a defined extraction speed in the second pot because that's very critical for controlling the solder thickness, regardless if it's a through-hole or surface mount part. When you're retinning QFNs, coplanarity can become an issue because you can see by looking at the bottom view, this large central grounding pad in the middle, there's always a tendency for the meniscus to form quite high on that grounding pad versus the individual terminations. So you have to watch that very carefully when you're retinning QFNs. QFPs, you can retin them down to 6 by 6 millimeters large as 50 by 50. There's a video coming up that shows that. We can retin QFPs down to 12 mil pitch with bridge-free results. Bottom terminated components such as QFNs, DFNs can be retinned down to 3 by 3 millimeter with a lead pitch down to a 0.5 millimeter. Again, the key is on those small little QFNs, that central grounding pad, there's always going to be, because we can't change physics, there's always going to be a tendency for a solder meniscus to be higher on that central grounding pad. We're able to control world-class coplanarity of 3,000ths. Again, it's just the physics of molten solder on that grounding pad. Here are just some still images of retinning a surface mount component and some true hole parts. The special application on the bottom is removing gold from lead frames, which is also one. Component retinning, you can pretty much do any through hole part. Here's an example of pin grid array. Surface mount parts, we can go down to an 0402. Pretty much any surface mount part, leadless part, can be soldered, retinned rather. Flat packs, such as a T-SOP, again, can be down to 12 mil pitch, can be retinned. Any through hole component that you can fixture or grip, you can retin. Large special components, you need to have some fixturing, but that's easy to do. Surface mount, again, whether it's LLCs, PLCCs, chips, SOTs, anything can be done, again, with fixturing. Fixturing is critical because you're gonna retin maybe 20, 10, 100 components at a time, and you need to maintain parallelism with the molten solder bath, just as you do in a wave machine. You need to control the immersion depth and extraction speed, so you have to fixture those parts so you have consistency. Multi-sided parts like QFPs, need to be done with a multi-axis actuated robot because you have to get all four sides and they're somewhat delicate, can't damage them. This is a video. I hope it's not too grainy. This is a retinning a through-hole part where a part is fluxed and then there's hot air convection preheat. You're soldering, you're retinning several parts at once. You control the depth of immersion in the flux. The preheating is controlled. The solder entrance speed. Here the components are being put in the first or scavenging pot. You'll notice they're being, there's aggressive movement in there, and that's to remove all the gold or oxides. Then the parts are refluxed, and then they go in a second pot. You'll see a draw skimmer removing the top materials, and then you'll notice very carefully when the parts are extracted that the extraction speed is controlled very accurately. You can see that little hesitation there. That's what controls the solder thickness. This is a drag solder operation that's used to retin several surface mount components. We're just showing an example of tinning several at once. In a production environment, you'd have the entire fixture filled. This is just partially filled. Here's an example of retinning fine pitch QFPs. They're pulled out taken out of a jetic tray after they're have to be fluxed and preheated. You notice you have to flux each one of the sides individually without touching the flux to the plastic body. So you have to rotate and articulate it. The part is then heated with convection reflow, and you'll notice it's, again, you have to solder dip in each side and pull away on an angle to minimize bridging. And you'll see that it's a very delicate operation. We can go down to 12 mil pitch. Some people buy machines to do retinning. I think what's much more common these days is people are outsourcing the retinning to a service supplier. ACE offers retinning services, and I'm not going to read it. There's pretty much an example of everything that's done. What's interesting is there's a difference between retinning suppliers. This is an example. This is a 64-pin, 20 mil pitch QFP that's done in relatively high volume, let's say, 1,000 plus per week on an ongoing basis, and you can see the difference between two different tinning suppliers, service suppliers, in terms of one has pinholes and residues, and you can see a significant difference in defects per million opportunities in bridging, again, between two suppliers. And that's it, Bob. Open it to questions.
Well, thank you, Bob, for that information. You did have quite a few questions, like in the first session that we had. First one is, what should you expect to pay for a wetting balance test done as a service? And part two is, can you compare machine A results versus machine B results?
I think they're referring, when they say A and B, they're referring to dip and look versus wetting balance, right?
I think this one was more, a wetting balance, test done at one supplier versus a wetting balance test done at another supplier. Can you those two? Are they like results?
Right. Okay, let me answer the second part first. Consistency between one wetting balance machine and another, one supplier and another, that's a function of calibration because it's a load cell. That's really the most critical thing. In terms of accuracy, some have a little finer resolution, and they're all measuring the wetting force in newtons, or in some case even finer than that. Can they measure in millinewtons? It's like anything. It's the resolution. It's like a pick and place machine or so forth. And the other one is how accurate is it recalibrated. So if you got a good machine that has good resolution on that load cell and it's calibrated routinely, you're going to have pretty good results. One supplier versus the other, I'm not familiar with all 4 or 5 of those wetting balance suppliers to really say across the board, but it comes down to, again, the resolution, the accuracy, and the calibration. dip and look tester is pretty easy. You're controlling it in flux and molten solder for a predetermined period of time, dwell time, and then it's up to an operator to look at the sample. The advantage of both is, again, as we said, that the wetting balance is something you want to do in a lab or qualification test, like you're qualifying a new component supplier. The wetting balance, or the dip and look, is something that's very quick and fast and can be done on the shop floor. And if you have known good samples, like some color pictures taken through a microscope to show your operators, they can very quickly say yes, no, this is good or bad, or so forth. So.
Yeah, this kind of sounds, Bob, like what we had in the first session. How do I tell who has done a better job, in quotes, as being a tinning service supplier? Any suggestions?
Well, the answer to that is to have that tinning service supplier provide a detailed report, or you can go out to a lab and do it yourself, but you want to measure, how good is the solderability before and after. You want to measure your thickness of the coating they're putting on. Again, as we showed this previous slide, no runs, no grips, no errors. You want to look for flex residue. You certainly don't want to have that. You want to look for frequency of bridging, consistency. Often, the tinning outsource suppliers, people look at, I hate to say this, but some people look at price only. There's a big issue. There's delivery, but the quality is basically how consistent is it? What's the coating? What's the wettability? In most good tin suppliers, they're going to give you a first article inspection with every single lot they do for you. They're going to give you test results, and you can even ask them to do the wetting balance before and after. I don't think I answered the question, what do you pay to have a wetting balance test done? I think the answer to that, the price will vary. You can go to a FA lab, and they may have the same wetting balance machine that a tinning supplier has, but my guess is that charge per hour would be significantly different.
Bob, is there any?
I guess.
I'm sorry.
Go ahead. No, so I guess I'm saying on what would it cost to have a wetting balance test. I think it's going to be all over the map, depending if you're going to FA lab or you're going to a tinning house.
Bob, is there any standard for the manufacturers of components, i.e., so component manufacturers, in terms of solderability testing? In other words, when they send me parts, should I expect them to already have done some kind of solderability test?
Well, that's a very excellent question, and it comes down to, it's sort of like that carton of milk or carton of yogurt. When it left the factory, it's perfect. The problem is it goes through distribution channels, it sits on a warehouse, it sits in your warehouse, not always in the best of conditions. So the solderability from when it leaves the component manufacturer to after it goes through shipment, storage, et cetera, shelf life, is going to be totally different. So it's kind of like someone said, EPA mileage on a car, when you look at the data sheet, you can duplicate that if you coast downhill with the engine off and a tailwind. So it's kind of I hate to say it's a meaningless number, but it's kind of an irrelevant number.
This user says, how have you seen people store last time purchased components after retinning is done?
Well, that's a good one. For example, we have a client right now that has parts that have been sitting on the shelf a long time. They're in the business of, they have to delve into a lot of end-of-life and obsolete parts. Once they're retinned, they try to consume them as quickly as possible. The other thing you could do once you've retinned them, if they're not going to use them for right away, is you can put them in a nitrogen cabinet. You certainly don't have to purge it to the level that you would for an MSL4 or so forth, but a nitrogen cabinet with a little trickle supply isn't that expensive. That's the best way to do it if you're going to have those parts that once they've been retinned, if they're not going to be consumed for a long period of time.
Last one we have here, Bob, is how do I get a hold of the GEIA standard 0006 that you mentioned in your presentation?
You can purchase it. It's under license. It can't be reproduced. You can go to the, I think it's the ANSI, and you can purchase it from them.
Go to the ANSI website and buy it there, huh?
Right. I think it was issued in 2008, if I believe, and there hasn't been an update since then that I'm aware of. But you can purchase it.
Oh, another one, last one. Okay, so I lied. There's one more. Do you expect to see differences in cost between the wetting balance test E1 compared to G1? I don't know what the user's referring there to. E1 to G, what they're talking about?
Maybe are they talking about dip and look versus wetting? No, read that again, Bob.
Do you expect to see differences in cost between wetting balance test E1 compared to G1, like George 1?
I don't know what E and G means. They said cost or results?
Cost.
Okay. In most cases, if you're doing it yourself internally, the cost is the time that it takes to do it. Wetting balance probably takes 4 to 6 times longer to perform. As far as cost, if you outsource it, like I said before, if you go to a FA lab that has a wetting balance tester, their hourly charge is going to be a lot higher because they probably have SEMs and everything else. If you have a tinning house that has a solderability tester, wetting balance right there, their cost is going to be lower. Don't quote me on this, but I think I've seen as low as like $50, and it might be a lot higher if you went to an FA lab. So it's kind of hard to do because I haven't really priced it. But it's going to range. It's going to be a function of what other businesses do those people have to keep their people occupied. It's like being a CEM, right?
Yep. I asked the user for a further explanation. If we get one while we're still on, maybe there will be a clarification about it.
Right, but I don't know what the E and G was.
Can't help you there. Sorry.
Can you guys hear us? No.
Yep, I can hear you.
Oh, you can hear us. Yeah, these are the tests in the J standard 002. So they have different wetting balance tests listed. So like test F1 is for test component, and then test G1 is wetting balance globule test.
Yeah, you must be on a speakerphone. At the end, you tailed. It was kind of hard to understand. One was you said the 2 different tests, but did you repeat that?
Yes, it's the J standard 002 solderability test. So they list several different types of tests, for wetting balance. So one of them is test F1 for leadless components, and then there's a new one which they call test G1, and it's listed as globule test. And we believe this is the one that has been.
For just a second. That was tough, Bob. Sorry.
Yeah,
that was very tough.
Yeah.
Yeah.
Can you put that on chat for us, please?
Yeah.
Yeah. It's really, really hard with the background echo. It was really hard to understand that. If you could, chat or email that in.
Okay.
We'll make sure to answer all the questions. And again, all the attendees will get the slide deck, Q&A at the end of this session, and then a link to the recording. All right, so yeah, I'm trying to mute all the remnant audio there, Bob. So sorry.
Yeah, that echo was pretty nasty. So.
Yeah. So thanks again for joining us here at BEST this afternoon, and all the best to Bob Klenke, and thanks very much for your expertise this afternoon, Bob.
Okay, thank you, gentlemen. Thank you, everybody.
Great. Signing off. Thank you.